In the previous video, we looked at what the ancient civilizations thought the Earth and our solar system looked like. By the time we left the story, the Greek had settled on a spherical Earth based on philosophical discussions and simple observation, an Earth that was the center of the solar system. Now we continue the story looking at the scientific method applied to these philosophical constructs. Other than philosophical discussions, people realized that the Earth's surface was curved due to a simple observation. Ships were observed to disappear over the horizon, with the hull disappearing before the topmast. In addition, ancient astronomers could observe the moon and sun having a round shape using their eyes, and the shadow of the Earth cast on the moon during a lunar eclipse was also curved. As shapes such as a disk could display shadows ranging from round to oval to a line, the sphere was seen as the only shape that could describe this observation. In 250 BC, Eratosthenes and Aristarchus managed to build on the worldview developed before them by using simple geometry to estimate the size of the universe. Assuming a spherical Earth, Eratosthenes used simple geometry to calculate the circumference of the Earth. He knew that on summer solstice, which is a predictable but special day, at noon at any point on Earth, the shadow of the object will disappear as the sun's rays will be parallel and perpendicular to the ground. He planted a stick in the Egyptian city of Syene, and at noon the stick would cast no shadow. At exactly the same time, a similar stick in Alexandria, which is to the north of Syene, cast a shadow at an angle of 7 degrees. Using the distance between Alexandria and Syene, which is 4,900 stadia, approximately 784 kilometers, according to the Egyptian pharaoh's scribes, and simple geometry, which is shown in the image, he calculated the circumference of the Earth to be 40,320 kilometers, which is very close to the actual value of 40,030 kilometers we know today. This helped create the first maps of the known world, crowning Eratosthenes as the father of geography. Aristarchus also tried to figure out the size of the Earth by measuring the Earth's shadow on the moon during a lunar eclipse. He also measured the sizes and distances of the sun and the moon. He concluded that the sun was 6 to 7 times wider than the Earth, and thought that the larger object should have the most attractive force, and hence be the center of the universe. Yet his heliocentric ideas were not really picked up by other philosophers at the time. At the time, the Sun, the Moon, and Mercury, Venus, Mars, Jupiter, and Saturn were the 7 objects that could clearly be identified in the night sky. Moreover, their relative motion could be tracked. For example, the Moon, Mercury, and Venus could be seen to pass in front of the Sun. As such, these objects could not all be on the same celestial sphere along with the other stars. Plato had proposed that these planets followed perfect circular orbits around the Earth. Circular orbits were selected based on the reasoning that all things in the heavens should be perfect. Heraclides in 330 BC placed these planets around the Earth in a way to describe the observations, developing the geocentric model of the solar system. Aristarchus in 270 BC, based on what we discussed just before, developed an alternative model based on the same circular orbits, but this time with the Sun at the center and the Moon orbiting the Earth to explain eclipses, giving rise to a heliocentric view of the world. Aristarchus' model was ruled out by philosophers at the time on the basis of 3 thoughts. The model said that the Earth is in motion around the Sun, but philosophers could not feel any motion. This issue was not resolved until Newton's laws of motion were developed and used to explain the relative motion of objects with respect to each other. If the Earth moves on a circular orbit, then nearby stars should show parallax, a relative shift in the position of nearby stars relative to a distant star. But this could not be observed. Hence, Greek philosophers prefer the model that with the crystal celestial sphere, where there will be no parallax. Aristarchus claimed that the stars are so far that the small parallax could not be observed with the naked eye. In fact, the parallax was not measured until 1838 by Friedrich Bessel. The geocentric model also seemed more natural to philosophers. as the egotistic idea of the Earth being the center of the universe is very appealing to humans. Ptolemy in 200 AD developed a mathematical description of the geocentric solar system known as the Ptolemaic system, helping standardize the Aristotelian description of the universe. His 13-book treatise called the Almagest was a synthesis of all the work done before him in Babylonian and Greek astronomy. His work was the standard description of the universe for over a millennium, being used by European and Islamic astronomers to predict the motion of the stars. In his first book, he provides reasoning in support of a geocentric system with an immovable Earth. These include the following. Like those before him, Ptolemy believed that all bodies fall to the center of the universe. As objects on Earth would fall down to Earth, that it made sense for it to be the center of the universe. If the Earth rotated every 24 hours, then an object thrown vertically upward should not fall back to the same place, but we observe it to do so. He was also able to show that no contrary observations to his model existed. In his model, Earth is the center, followed by the Moon, Mercury, Venus, Sun, Mars, Jupiter, and Saturn. The fixed stars, which were farther away, were assumed to be on the prima mobile, the outer sphere of the model. However, one problem they faced was the observation of retrograde motion, where outer planets seemed to move backward. To explain this, like Hipparchus before him, he relied on a system of different and epicycles or one of movable eccentrics. Each planet was assumed to move on an epicycle, which in turn moves on a larger different. Motion on both circles is clockwise. The difference had a center called the eccentric that was located slightly away from the Earth. His model predicted the apparent motion of all planets and began the first mathematical framework to understand nature. With Ptolemy's model, cosmology goes from the mythical to the science-based. The Greek philosophical tradition was that nature is understandable rather than under the control of deities. This concept also forms the basis of science. Some argue that the greatest gift of the Greek was the philosophy of rationalism, that the universe can be expected and understood. The Middle Ages, from the fall of the Roman Empire to the 14th century, were somewhat of an age of scientific stagnation. Yet there was some intellectual progress in Europe, which flourished during the Renaissance, and in the Middle East and India as well. With the burning of the Great Library of Alexandria in 272 AD, a lot of the astronomical data of the time was lost. During the time, the Catholic Church preserved the cosmological ideas of the Greek and adopted the Aristotelian worldview as one of its own. The Church defined heaven to be the realm of perfection as per Plato's theories. They also adopted Aristotle's worldview, adjusting it slightly with an unlimited universe instead of a limited one, which is more in line with God's infinite power, and a beginning for the universe that was creation. In accordance with the Christian belief, the universe cannot be heliocentric, so the geocentric model became prominent. The Ptolemaic system, which was geocentric and predicted movement of celestial bodies accurately, was also adopted. As described in the Divine Comedy, the Aristotelian model in Christian view is adjusted by the addition of a ninth primum mobile, which accounts for the movement of all planetary spheres. Beyond this sphere is the spiritual universe, the world of the supernatural. The purgatory is between the surface of the Earth and the sphere of the Moon, and hell is inside the Earth. Outside the Church, while the concept of the spherical Earth was prominent, mentioned in Norwegian books in 1250 AD, the disc shape had also been preserved, for example in French texts of the 12th and 13th century. Portuguese navigation down the coast of Africa in the 1400s and Magellan's global circumnavigation in 1521 provided practical support of the spherical model. As the intellectual authority of the Church declined, it was replaced with a style of thinking focusing on the connection between ideas and facts, or the scientific method as we know it. Muslim astronomers generally accepted the Ptolemaic system and geocentric model, yet from the 10th century they started to doubt the model. Doubts were held regarding the immobility of the Earth, it being the center of the universe and it not rotating around its axis. By the 12th century, Al-Zarqali hypothesized that planets such as Mercury might be on elliptical orbits, and Al-Bitruji developed a model without the equant, epicycle, and eccentric of Ptolemy, albeit less accurate. The Parallax school of astronomy aimed to resolve the issues with the Pitoni Model from the 12th century to the 14th, going to the extent of developing models equivalent to Copernicus's and discovering Earth's rotation through observation. Many had challenged the geocentric model of the Church. Copernicus managed to do so and get his model published in the 15th century as On the Revolutions of the Heavenly Spheres. His success was based on the fact that the Church was weakening in Northern Europe at the time and hence allowed more diversity in scientific thinking. In addition, better understanding of the concept of inertia and motion was starting to undermine the concept of an unmoving Earth. A rotating Earth explained the diurnal motion of stars in simple sense and paved the way for an Earth revolving around the Sun. The heliocentric model was not just an improvement but a paradigm shift. Copernicus's model had some basic assumptions. The Earth was not the center of the universe, but the center of the local gravity and the Moon. The Sun was the center of the solar system and all planets revolved around it. This would explain the retrograde motion of planets automatically. The Earth rotates around itself in this model, yet Copernicus kept Aristotle's celestial motion in perfect circles. As a result, each planet was said to move on a moving sphere to explain longitude motion, though fewer spheres were needed as retrograde motion was already accounted for. Despite these advances, Copernicus still relied on epicycles and difference to explain retrograde motion, even more so than Ptolemy. So the model was more complex. His tables were as complex as the other model, and as the model also clashed with the natural philosophy and scripture, it was not accepted by all. Copernicus's model contradicted with biblical understanding of the universe. Yet, when the model was presented in Rome, the Catholic Church showed interest and encouraged publication of the theory. Tycho Brahe in the 1580s built the Danish observatory and measured the position of planets and stars to the highest degree of accuracy, developing the first modern database of astronomical data. Based on these observations, he was able to show that the Sun is much farther away than the Moon from the Earth. Brahe was also a proponent of a geocentric view of the world. First, at the time, it was hard to believe in a moving Earth, as the force required to move the Earth seemed impossible to the average medieval philosopher. In addition, Brahe could not detect any parallax in the stars, concluding that the celestial sphere was immeasurably large. His attempts to estimate the size of stars led to star sizes larger than the modern size of the Earth orbit. This was due to the blurring effect of the atmosphere, which he had not accounted for. Finally, he was against the heliocentric model on the basis of religious views as well. To improve the geocentric model to match his observations, Brahe adjusted it. At the time, Mercury and Venus could be seen to behave differently from the outer planets. Mercury and Venus were always a few degrees from the Sun. To resolve this, Brahe proposed that the inner planets were orbiting the Sun, developing the geoheliocentric model, also known as the taconic system. In the 15th century, Somayaji, an Indian astronomer, developed a computational geoheliocentric model in which the planets orbit the Sun and the Sun orbited the Earth. The Earth also rotated around its axis in this model. This model was accurate in predicting the heliocentric orbit of inner planets and had similarities to the Brahe model. It was accepted by Indian astronomers for a time. Johannes Kepler was a student of Tycho and used the database developed by Tycho to extract the laws of planetary motion based on a heliocentric model between 1609 and 1619. These laws ended up resolving the issues of the heliocentric theory requiring epicycles by proposing elliptical orbits based on the observational data. With elliptical orbits, the orbital motion of planets could be completely described mathematically using 6 elements. Using his theory, Kepler was able to predict the transit of Venus in 1631 for the first time. This success became evidence that the geocentrists could not ignore. While Kepler's laws provided the mathematical description, one could argue that they were just a computational trick to describe a geocentric system. Galileo in the 1620s developed the laws of motion focusing on acceleration. He used his observations using the newly developed telescope to show that a geocentric universe could not be. Galileo could observe spots on the Sun, mountains and seas on the Moon, and many stars making up the Milky Way. This was inconsistent with the concept of perfection and being made up of aether put forth by Plato. In fact, one could argue that the imperfections on the Moon and its Earth-like look might mean it is made of a similar material to Earth. He also saw that Venus had phases and its apparent size changes with its phases. This is not possible in a geocentric system. Also, Jupiter has moons, which shows not everything orbits around the Earth as the geocentric model suggests. Galileo's discoveries and Kepler's laws provided the full kinematic description of the solar system, telling us about positions and motion. Yet it does not shed any light on why the universe behaves the way it does, what causes the motion of the planets, or the nature of stars and what is beyond them. This means a dynamic description of the motion and its causes are needed. In terms of the laws of motion, Galileo realized that falling objects accelerate at the same rate irrespective of their size or mass. Using inclined planes, he developed concepts of motion in terms of velocity, which is also a state variable for any object has it. He developed the idea of the force as the cause of motion, and that objects resist change in motion or have inertia. Following Galileo's writings and his attempts in his book to explain the heliocentric model using scripture, a papal ban was created on all writings supporting the Copernican system, a ban that stayed in place until the 18th century. The main advances in understanding motion came with Newton, who expanded Galileo's work to explain the relationship between energy and motion. Newton introduced the concept of acceleration as a change in velocity caused by the force. He also clarified inertia as the resistance to change in velocity. Momentum and the law of conservation of momentum were all other concepts introduced. Using these notions, Newton developed his laws of motion. The first law, which says a body at rest or moving at a constant velocity will maintain its state in the absence of external forces, and has to do with the concept of inertia. The second law, which says should a force be applied to an object, it accelerates it, and has to do with the relationship between force and acceleration. And the third law that says for every action there is an equal and opposite reaction, which basically connects the reactive nature of forces with respect to each other. These laws gave rise to the concept of a clockwork universe, where the total momentum of the universe is conserved and all interactions redistribute this momentum. God is the initial cause for the system to tick, and it keeps ticking. In 1687, Newton was able to show that the force of gravity is responsible for the orbit of planets in the solar system. According to Newton's understanding, an object like the moon orbiting the Earth would leave its circular motion unless another force acts on it to keep it within the orbit. Using this idea, Newton was able to derive a mathematical description of gravity and explain the observation of Kepler using mathematics based on the law of gravity. This finally introduced gravity as a force that gives rise to the motion of planetary bodies, and explained why the atmosphere, for example, sticks to the Earth. Empirical evaluation of these laws eventually gave prominence to them. One of the issues with heliocentrism was the lack of a parallax. Finally, in 1838, Bessel measures the parallax of a star successfully, disproving the claim of lack of parallax motion, which was the basis of the Pitoni Model. Observations by Herschel and Bessel in the 18th century showed that the Sun, while near the center of the solar system, is not the center of the universe, which was also supported by gravitational models. Over the course of the 18th and 19th centuries, the status of the Sun as merely one star among many became increasingly obvious. By the 20th century, even before the discovery that there are many galaxies, it was no longer an issue. So as you see, our conception of our Earth, solar system, and the universe is not something that came about overnight. Many scientists and philosophers have discussed different shapes and forms and developed a self-consistent model. In fact, the most important point here is self-consistency. Earth is only one of the many different objects around us whose behavior needs to be explained using physics. The shape of the Earth and its motion follows classical physics, principles in physics which have passed the test of time. Of course, there are exceptions to these rules at other regimes and at other sizes and shapes of objects, but we cannot neglect that these rules work and they make objects around us, like a car, like some of the parts of your phone, work as well. Now, despite this, there are people that believe that this model is not true, that some of these rules from physics are not really rules. In the next video, we will take a look at our general theory about the universe and at those who feel this is all a hoax. See you next time.